Good afternoon. Hello everybody in the world of physics. This is a little proof of an equation that we use a lot in physics year 13, simple harmonic motion. We've got a few people away, and also down the track we could possibly use this again. So what the plan of attack is to find a proof of this equation, which is given on the year 13 resource booklet in the exam. And this is my take on how we can find it. And I did this on the 28th of March 2022. So this formula is given in the resource booklet, and it's nice to know the origin of it. So therefore, instead of just believing things that people give you, you can see them built up and proven. Alrighty, so we start with a reference circle, and also we put in the horizontal. This is not the orientation of the simple harmonic motion oscillator. This is the angle, and we start at the 3 o'clock position. Measuring the angle around there, that's the angle theta is omega t. This is the simple harmonic motion oscillator. It might be a pendulum, it might be a mass on a spring. It's going backwards and forwards on this line, and it is in the same, its height, its displacement is the same as the vertical displacement on the circle. So at this particular moment, at this precise moment, it's going up, and we know that because the simple harmonic motion, get myself a little pretend laser pointer here, the simple harmonic motion reference circle marker is at this point, and everything rotates in the anti-clockwise direction. So we can draw in the velocity for that there, and the previous one, this little Vs, this is the velocity, instantaneous velocity of the simple harmonic motion oscillator. I say instantaneous because it changes all the time. Now this is the instantaneous velocity of the thing that's doing circular motion at that moment, Vc, circular motion. And I'd like to draw your attention to these two vectors here. Vs going up, Vc at an angle. And if we blow those up, pull out those two vectors, make them bigger, they look a bit like that. I haven't drawn in a horizontal line that connects the tip of the two arrows because there's no need for it to be there, but there is a right angle triangle in that triangle, right angle in here at the tip here across to the top. So that means we can say that the cosine of this angle is the velocity of the simple harmonic motion divided by the velocity of the circular motion oscillator at that moment. And then we do a complicated step called swapping sides. And then we know that theta is omega t, so we have Vs divided by Vc as cosine of omega t. And that's cool. Then we multiply both sides by the velocity of the circular motion reference circle object. And we get Vs equals Vc cos omega t. But then we use Vc as omega r, that's from the circular motion stuff. And then we also know that in a reference circle in simple harmonic motion, the radius is the amplitude of the motion. So Vc equals omega a. Finally, we have Vs equals omega a cos omega t, which is what we're looking for. It's on the formula sheet, and that's where it comes from. Kia ora, folks. Thank you very much.